All right, welcome back to the second session of this workshop. My name is Remco van der Hofstad. I'm one of the organizers, and it's my great pleasure to introduce Mihyun Kang. And she will be talking about local limits, and then in particular about the interplay between the locality and the global properties of the random graph. Please go ahead, Mihyun.
Thank you very much for the kind invitation and introduction. Indeed, I was not sure which talk I should give because the theme of the workshop or the whole semester program turned out to be either graph limits in that sense or local weak limits. So I could have talked easily about chromatic number of dense graphons in the sense of the Dan Graz talk. But then I realized that something else is going on in this whole program, namely the local weak limits. If you were in the boot camp, we learned a lot about this, how important it is to have a good local weak limit by the talk of Suvik. So that motivated indeed this talk and the title in particular. So I will be focusing on the very sparse random graph, sparsity, meaning that the average degree is always constant. And then I will mostly focusing on this interplay of local and global structure. It can be anything. But then what is motivation of such a title is the following, that by now we all know that since the seminal work of Erdos and Renyi, of course, the giant component is one of the leading themes in the theory of sparse random graphs. And it has long been observed that the giant component is analogous to the survival of the associated Galton-Watson process. Galton-Watson process is something global. And on the other hand, this crystallizes, this kind of analogy crystallizes the kind of this interplay between local and global structure because of the emergence or the threshold for the emergence of giant component is indeed determined by the average degree, which is kind of a local thing. And this kind of motivates. And in particular in this talk, I will talk about two directions from local properties to the global structure, meaning that you look at the local neighborhood, we know something about it. Can we say something about the global structure, such as the giant component? We will see that there is a limit, but also there is a way to get out of it. Turning our gear, I will also talk about how the global structure or the global constraints imposed on a random graph changes or affects its global structure. Of course, when I give a talk about sparse random graphs, it's so much tempting. And not to talk about the Erdos and Renyi result is something that I cannot avoid. I always start from that. So let's start from a very basic classical result about the Erdos and Renyi random graph in the first part, namely the emergence of the giant. By now we all know, but let me recap. I will not talk about the original Erdos and Renyi random graph model, namely the uniform model GNM, but I will switch into GNP by now because it's easier to present. So we will think about, look at the Erdos and Renyi random graph, or sometimes we just call binomial random graph to distinguish it from the uniform model anyway. So GNP, and we will be considering the number of vertices contained in the largest component. And we let always a degree to be average degree D, which is of course equal to P times n-1 in this model, because for each vertex we have n-1 potential neighbors, and each with property P will be indeed a neighbor. Therefore, this is the average degree, and we will always consider it's a constant. And one of the most famous results by Aldous and Renyi is about that. If the average degree is smaller than is smaller than 1, with high probability, meaning with the probability tending to 1. Let's see. All the components are small in the sense that they are at most of logarithmic order. On the other hand, if it is larger than 1, we do have a unique giant component, unique largest component of linear order, which is sometimes called the giant. Of course, by now, this is not a surprising result in view of, let's say, the universality principle of the population theory, which says that the cluster threshold of the giant cluster is indeed determined by the local structure. And also its analogy to the Galton-Watson process. In the Galton-Watson process with the mean D, we know that if average degree D is smaller than 1, number of children, expected number of children is smaller than 1, the process dies out. On the other hand, if the expected degree is larger than 1, the process continues forever. And indeed, this kind of analogy can be made rigorous. And using the survival probability of the Galton-Watson Poisson tree or Galton-Watson Poisson process with Poisson D, we can indeed determine the precise order, asymptotic order of the giant component as the solution of this just transcendental equation. This exactly marks the survival probability of the force. There's this analogy. To make such an analogy work, we have learned from Suvik's talk, you need to work harder. It's not just coupling with the coupling of the component exposure process with the Galton-Watson tree will not be enough. We have to apply the first and second moments as well as so-called sprinkling argument. So in other words, we need to a little bit work harder, although we know that there is this analogy to the Galton-Watson process. And that's the one thing that kind of motivates the rest of the talk. How such analogy is indeed was discovered was already in the Nonparametric paper about the random hypercube or populated random hypercube and so on. It has been a while, but it has been systematized partly due to Karp and later by other people. Yeah? So let me just give you why this was the case using a very rough idea of what the local structure is about. Everybody knows, but I'm just reminding you of what you might have heard about in the past. So we still have an average constant degree D, and let's choose one vertex uniformly at random from the vertex set of the universe. And you expose its neighbor. Of course, it's asymptotically Poisson, so the out degrees, the number of degrees born in there is the Poisson D, and you select one neighbor of the root. And apart from all this small dust, of course, this also has roughly Poisson D because it's likely that we will not expose too much, and so on and so on. So long as now it comes this ruse description of the local structure. So long as we do not go too far away from the root, yeah, it's kind of not far away from the root, kind of defines the radius of such a ball, which I will come back later. So long as we don't go too far, we know that the average degree or out degree of each vertex will be roughly Poisson D. Of course, this is a very loose description of a local structure, but we can formalize it. This very simple, basic, simple observation can be cast nicely in terms of the local reconvergence of the Benjamini and Schramm as well as by Erdos and Steele. Today we have heard about it already by Peter's talk and as well as in the boot camp. Yeah, what is it? I will formalize it. That contribution goes back to sets of people, Benjamini, Schramm, as well as Aldous and Steele. Basically, the object that we are looking at is the so-called rooted graph. Say it's a pair of a graph H and R. Basically, we are given a connected, locally finite. If you look at locally, it has the finite number of neighbors, or if you look at only the finite radius, number of vertices in there is finite. That's what we mean by locally finite. Globally, it can be infinite graph. Yeah. So connected and locally finite graph H, in which we select one vertex as a root. Just to visualize it, I have one vertex chosen. I look at it, and then I have this kind of strange thing. What it is the so-called ball of radius of R. So what is that? Given any parts the integer and any rooted graph, we will define an object, namely the ball of radius for L, which is the induced subgraph. Induced, this notation is induced subgraph, induced by the vertices of the original graph whose distance to the root is at most L. Namely, this will be the ball of radius 1, ball of radius 2, ball of radius, and so on. So we look at it. Such a ball will be an important concept to define this locality. Furthermore, we say two rooted graphs are isomorphic if there is an isomorphism from one vertex to the other. Isomorphism meaning that the H property should be preserved, yeah? As well as the root should be sent to each other. It's clear, right? It's a graph isomorphism in addition to the fact that the roots should be sent to the another. It's isomorphism. So now it's a kind of basic definition. Now I'm ready to define what local limit is. I'm not talking about the metric because it will be too much detail, I think. Huh? From the Christian stuff, we of course know that how you measure the distance between two rooted graph by the inverse of the distance, blah, 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 but I will not do in that formality. Yeah, so given a sequence of random rooted graphs, Gn, Rn, for each n, G1 Rn, G2 R2, we have a sequence of random graphs, rooted graphs. And we say another random rooted graph Z0 R0 or G or R something is the local weak limit of the sequence GRRN, we just denoted by such, if now comes the definition. For each fixed rooted graph H and HR, and for any integer L, the probability that the ball, this is my ball, the GNRN, the ball is isomorphic to the given rooted graph. The probability that the ball is isomorphic to the given graph converges to the probability that the ball in the limit, so another object G0 R0 is isomorphic to R and H. I could kind of have, if you look at it correctly, if I look at it as far away, some of the edges are different. They are identical. To this ball, I have drawn the same thing. So if I look at only the finite ball, they look the same, isomorphic to any given. Is it clear? Some people call it convergence in distribution, but as Christian said in his talk, this is kind of a weaker notion. It's better to have convergence in probability. There is such a version as well, if you are curious. One of the things that you can look up is the book by Remco. Yeah, so this is a weaker version, but nevertheless not interesting. It's still interesting. But if you want to prove something stronger, you need convergence in probability, but we will be happy with it. I will be happy with it. It's clear what we are doing. Now, using this terminology, the observation, this loose observation about the local structure of Erdos and Renyi can be written very simply. Now looking at the thing, you might be able to think that I'm talking about the sparse random graph. We know that if the average degree is smaller than log n, we know that the graph is not connected. But how can we define a local limit if the graph itself is not connected? Then indeed, we define such a thing as the local limit of the component that contains the root vertex. So if the world does not consist of one single connected graph, but consists of many components, the definition of the local limit was equipped with this random vertex, and we will select one vertex from the random from the universe, and we will see where it lands in. The local limit of the component containing the root. Clear? Now, using this terminology, now we are ready to formulate just in one line in this fashion. Same as we consider Erdos and Renyi G and P with constant average degree. It doesn't matter which, from 0 to infinity. And we select one vertex uniformly random as the root. Then the local limit of the Erdos and Renyi is just Poisson-D Galton-Watson tree. What is that? It's an infinite tree generated by a Galton-Watson process with offspring distribution Poisson-D. Very, very well known. It's kind of folklore, but the proofs you can find either by a paper by Dembo and Montanari or the book by Remco van der Hofstad, which will soon hopefully. GMP, we can say that. So I just write it, just a reminder what it means. Of course, if you understand this picture, you will see it often, but you can just think of this in distribution. Yeah? No questions? Now, okay, very simple observation. Why do we care about local structures? It's a very simple is anything, but I already mentioned it has to do with the local structure is related to the population threshold. Population threshold where the giant cluster appears, at least the critical value we can determine. Of course, if you look at the phase transition, you have to also discuss the critical window, width of the window. Window is not a local, it's kind of global. You have to look at critical exponents, which usually related in GNP, a number of tree components outside giant and so on and so on. Anyway, this is more global, but if you look at only the critical, so where giant component appears, namely the critical threshold, then indeed it has to do with local structure, even the average degree. And I don't need to go depth 2, it's enough to have depth 1. Another thing that I mentioned, I just bypassing, of course, the giant component. In order to study the size of the giant, usually there is a nice upper and lower coupling of the component exploring process by the so-called breadth as such. You look at always its neighbor, start from a neighbor, look at the neighbor, so-called breadth as such. And you can couple it from above and below by associated Galton-Watson branching process. Nevertheless, local structure, local limit itself is not enough to talk about the size and the uniqueness of the giant. It is related, but not. So in order to have the information that we had earlier, we need to use usually, it became standard. So I'm talking about standard method, usually first and second moment for the upper and low coupling of the associated Galton-Watson process. But then it says about there are potentially many large components, but then using the so-called sprinkling, you can say the uniqueness of the giant, merging them together. So there are, it became standard, but anyway, the starting point is, as I said, local structure. Second, the advantage of this approach, this local structure, is also that the analogy to the higher dimensional things are quite straightforward. You can have a higher dimensional giant component, which allows many overlaps depending on the dimensions. It can be really nicely extended, subject to some hard work, but it's usually technical nature. But then also similar idea can also be applied to structures with more little bit geometric. It's not exactly, but sort of geometric structure, like a hypercube, percolated hypercube. Similar idea can be generalized to there, and so on and so on. Yeah? Even the simpler random simple complexes, similar ideas can be applied. Local structure, and so on and so on. This is more combinatorial part. And now there are other kind of applications, so-called message passing algorithms. Today it was mentioned already by Petter's talk. There is a very nice book by Mezzad and Montanari on information physics and computation, in which there are many message passing algorithms starting from the local structure. Just to name a few, propagation, it has been studied a lot, for example, for the so-called random k-set, or random coloring, or any random constraint satisfaction problems, and so on and so on, many optimization problems. And also there is a simplified version, which is so-called morning propagation algorithm. It's really simple. If you are coming from the combinatorics, it has to do with the so-called peeling process. You peel out the things that you don't want to see, and you realize that you can construct something. Such a thing is so-called K-core, which is the maximal subgraph, whose minimum degree is at least K. So you can achieve them by deleting the vertices degree and most K-1, and such a filling process can nicely be interpreted as the so-called morning propagation. You just send the messages from the bottom to the top. And also recent work, the rank or the nullity of a parity matrix or sparse parity matrix can be also studied by morning propagation. And I put here ... because this is really a lot of things are going on in this direction. So not only the spin models, but other things. Yeah, this is why we do care about the structure. One thing, and now I want to switch from global to local. Namely, we want to impose some global constraint to a random graph. Of course, one way is imposing the girth information that we have seen from Petter's talk, but also not only the girth restriction, maybe you impose even more restrictive constraint. Namely, I want to consider only the planar graphs, or I want to consider the graphs that can be embedded on a surface without crossing edges. Such global constraints had an effect to the global structure, namely the size of the giant and outside the giant. But then in turn, it does have an impact or affects also the local structure. Indeed, this I could have studied from here, but at first I want to just give you some background on the local structure. Any questions? Why we care about such a global constraints also comes from our master's result some 6 years ago. So already in the earlier paper, Erdos and Renyi proved the following. Of course, they proved the things in GNM, but it can be translated in the GMP. I want to consider the same model. That's why up to here about the Erdos and Renyi. So if consider the Erdos and Renyi random graph, or the so-called binomial random graph GNP, when the average degree is constant, not only the giant component is small, we know that if the average degree is smaller than 1, then each component is either a tree or it contains, it's unicyclic, meaning that it contains only a single cycle. Therefore, it is planar with high probability. On the other hand, if you increase the P average degree larger than 1, then it contains, we have seen that unique giant component, but that giant component contains at least 2 cycles. We sometimes call them complex. Furthermore, not only it contains 2 cycles, it is not planar any longer. So there are topological copies of so-called K5 or K33. So it is not planar. So kind of this motivates some of the people. What can we say about random graphs with planarity constraints already? If you think about it, there is a natural binomial model with restrictions of the planarity. If you think about a little bit more, that is very crucial to have transition to direct comparison with the GNP and with the planarity constraints. Because of the edges are not any longer independent, it's not an easy thing. So switching from GNP to the uniform GNM is easy. 2 models are almost essentially equivalent. It is continuous if the number of edges in these models are the same, let's say, for simplicity. But there is no direct such a thing. So there is the switch from one model to the other in case of planar is not simple. On the other hand, the planar graphs has nice structure. So what is more convenient model in case of the planar graph is indeed a uniform model. It has to be a lot of counting things going on. So I'm switching the model from binomial to non-binomial on purpose indeed. So I could have studied with the GNM, but I want to mention that because of this edge dependency, the things are much harder. So what I want to do in the rest of the talk, we will look at the random graphs with the topological constraints. And we will look at how there's a topological constraint such as being planar, or it can be embedded on a sphere without crossing edges, how much it affects the global and local structure of a random graph, such as the giant component or the component structure or the local limit. Clear the questions? To do that, let me set the scene. That G, it's not a graph. It's a G will be denoted kind of genus. G will be any non-negative integer. Unless SG be the oriental surface or 2-dimensional surface with G handles. It's with torus or 2 torus and 3 torus, yeah, G handles. It's clear, right? And the model that we will talk about, or the class of graphs that we will talk about is the set of all vertex labeled, the simple graphs on n vertices with exactly n edges, but they are embeddable of the sphere. In the physics community, often they talk about planar graphs, meaning planar maps, meaning that it's already embedded. We are not talking about the embedded things. They have a potential to be embedded. Yeah? So there is a distinction a little bit. So we think about such a model and we select one uniformly random, SG and M. Simple observation is that the simplistic case of random graphs on a surface is when the genus is 0. This is just a planar graphs. Yeah? The graphs that can be embedded on a sphere without crossing edges. That's, of course, anything that can be embedded on a sphere without handle can be embedded on a sphere with 1 handle, 2 handle, and so on. So it's like incremental in terms of the genus. And if we don't have any restrictions on the genus, of course, they are the whole world. Any graph on n vertices and n edges. We can, having such a simple thing, we can turn our things, everything in terms of the cardinality, namely the counting things. That's how we are doing things, we will do. Very simple observations. The Erdos and Renyi result about planarity can directly interpret it in terms of this, right? The fraction of the graphs that can be embedded on the sphere versus to the total number of graphs tends to 1. So GNP or GNM is planar with high probability when the average degree is smaller than 1. So for any m between 1 and n over 2, so meaning that this is average degree equal to 1, fraction goes to 1. On the other hand, yeah.
I mean, when you had G and P and Smaller than something. I was thinking of D as constant.
D was a constant.
Now, do you want the ratio of M and N be again a constant?
I will restrict that. Yeah, exactly. I will talk about that. Thanks.
So then, why do you subtract 6 as it makes no difference?
Yeah,
because
they will be coming here. Exactly. That's coming here. So on the other, due to the Euler's formula, very good. Euler's formula, we will not have any graphs on a surface with then more than that many edges. Due to the Euler, we cannot have them. Therefore, they are 0. So the only case that are interesting to our point of view is the when the average is between 1 and 6. That's what I want to say. We will restrict on that. And furthermore, if I talk about random graphs on surface with the genus G, this is very lengthy. And because of the result that I will present, indeed holds for any genus in constant genus case. So I will just restrict myself to planar graph. To simplify the notation, and instead of S0 and M, I will just use P for planar. Yeah, that's the notation. P and M will be a random planar graph, chosen here from a random. I set this in. So another thing that is I have to mention is that it's not my invention. This kind of thing has been studied already. What kind of questions related to random planar graphs and random surfaces were already raised by Alan Fries in the 80s, but then it became more popular in about 20 years ago due to a very powerful and breakthrough, I don't know, but a very interesting result, because breakthrough happened later. Very motivating paper by results by Steger, McDermott, and Welsh about 20 years ago, in which they studied a lot about random planar graph, how you generate them, how you sample them, what is the connectivity threshold, and so on. So a lot of things were kind of initiated. Therefore, it became very popular during the last 20 years. But on the other hand, the model that they look at is the so-called n-vertex model. Not there, but also the generalization of their models. So most of the study on random planar graphs and random graphs on surfaces is kind of deals with the so-called n-vertex model, in which we do allow any number of edges. There is no restriction on the number of edges. Yeah, so just n-vertex chosen uniformly random. Then what has been proved is that indeed, typically a random n-vertex model is dominated by quite a dense regime, namely when the average degree is around 4.4. And from this planarity point of view, it's kind of dense in the sense that n-vertex model is quite stable, it's well-ordered, very stable structure, namely contains any given subgraph, subplanar graph as a subgraph, as well as the giant component is huge in the sense that it covers nearly all the vertices. Somehow it is far away from the Erdos and Renyi type sparse regime. Therefore, we will indeed focus on the regime, which is more interesting, is when D is close to 1, If you look at the N model, it's usually dominated by the later stage when average degree is 4. Nevertheless, in view of the Erdos and Renyi random graph page transition, some 10 years ago, or even, yeah, some 10 years ago, Tomasz Uchak and I look at what can we say about the page transition in a random planar graph. Yeah. So again, we look at the planar graph, we look at the number of vertices in the giant. It depends on the average degree again, but surprisingly, there are 2 critical periods. The first critical period is when average degree is equals 1, which is analogous to the Erdos and Renyi. We have seen that this Erdos and Renyi phase transition has to do with the average degree being larger than 1 or smaller than 1. That we have seen already. So the first one occurs there, analogous to the Erdos and Renyi. On the other hand, when there is a second critical phase, when average degree is equal to 2, which we haven't seen in the Erdos and Renyi and even hypergraph setting, it's a very unusual thing about planar graph, is when average degree is about 2, then giant component covers nearly all vertices. Already at the degree 2, this is, and in between, just a linear. So the fraction of the vertices in the giant is just about D minus 1. Straight line. Very strange vegetation is going on. And of course, this kind of a behavior affects also some other things. namely not only the giant component shrinks, but the second largest outside the giant will become larger. And indeed, as a whole, if you delete the giant component from a random planar graph, the outside, the so-called the fragment, sometimes called small parts or fragment, is critical. So there is this another effect going on due to the planarity penalty. The edges that cannot be in the giant component because of the crossing edges, potential crossing edges, has an effect outside, causing other critical behaviors even outside the giant. This was the global picture. First, we studied for planar graph, and we realized that we can extend it to any constant genus, but indeed there is even stronger version that you can extend such a result to any genus which is smaller than that so-called the contiguity threshold of Erdos, Renyi, and random graphs on a surface. Anyway, things can be done. As you can imagine, if you have such a straight line, it's unlikely that there is a very simple Galton-Watson branching process approach. Perhaps it's impossible to couple our giant component with rather simple Galton-Watson tree. So it motivates what they are then locally. I zoom in at some of the point and I ask myself how they locally look like. Is it Galton-Watson tree or something else? This motivated me, and indeed the answer is the following. I just restrict myself when the degree is between 1 and 2, as I said, because this is the way the things are interesting. Then indeed, if you select one vertex uniformly random from the whole universe, then the local limit of the random planar graph is a combination of two linear combinations of two types, either Galton-Watson tree with the Poisson mean 1, or so-called the skeleton tree. So skeleton tree is just an infinite path in which every vertex is replaced by independent Poisson 1 Galton-Watson tree. In some sense, Galton-Watson 1 tree is T infinity tree where there are just starting from one vertex. It's clear. So
what is this plus? I didn't understand.
Yeah, plus is a very strange thing because we are talking about in distribution, right? It's written here. What we might mean by this notation is just that for each fixed rooted graph H and any integer L, if you look at the probability, the ball of radius L of the planar graph, the probability that is isomorphic to a given graph tends to a probability that Galton-Watson 1 is isomorphic to that times 2 minus 1. This is number, yeah, this is a problem. Plus, the ball around the skeleton tree is isomorphic to the given graph scaled by d minus 1. So you need a little bit of digestion because this is not often. How do you make a linear combinations to infinite trees, right? But it's a kind of probabilistic. They defined in this fashion.
So that means if I condition to be in the giant component, it's like T infinity?
Yeah, exactly. Then this is indeed a kind of a proof. The proof idea is very simple. I told you. Indeed, this local limit comes completely from the global structure, as you said, because the way we define the local limit allows that. If you look at the quenched local limit, quenched probability, it will be more complicated, yeah? Because you have to divide by random effect of the vertex. It's not, this is this called the weakest version of the local limit. As you said already, you hinted, it really depends on whether this randomly chosen root vertex lies in the giant or the outside the giant. Yeah? So indeed, the local limit is indeed heavily depends on the global structure. I don't know the other way around, to be honest, because I came from that one, or maybe some cleverer younger people perhaps can come directly to the local structure of a planar graph, yeah, which I don't see yet. As you see, what we do is we look at the component structure of the planar graph. Again, set the scene so that we are all there. I always look at the random planar graph with average degree tending to D, which is between 1 and 2. So this regime 1, yeah, the straight line regime. And S will denote the small part of the random planar, namely you delete the largest component and look at it. It's sometimes we call it fragment, yeah, it's why I call it McDermott. And indeed, the fragment behaves similarly like a critical Erdos Renyi random graph. In case of the classical Erdos-Renyi, perhaps you all remember the fragment, namely the graph outside the giant, behaves like a subcritical Erdos-Renyi, the so-called dual principle, right? There is also Poisson process, the dual Poisson process. So there is a very nice theory behind the scene, but surprisingly, as I said, because of the planarity constraint, has an effect outside the giant as well. Therefore, the outside the giant, the fragment, behaves at the criticality. Yeah? But on the other hand, looking a little bit, going inspired by the proof of the Remco's local weak limit of the binomial random graph GNP, you can indeed realize that indeed it's not direct, but you can compute the things so that you can have a local weak limit of the uniform Erdos-Renyi graph as well. It's kind of easy. Easy exercise. Then using the local limit, we can also show that indeed, if you look at the fragment only, the local limit is just Galton-Watson tree with Poisson 1. Criticality. I select one vertex uniformly random. If you look at the local, question, no work. Just a little bit of a modification of the Remco's proof.
So I guess if Grimmett has shown that if you look at a uniform random tree, like Cayley's theorem, then that converges to.
Then it's a skeleton tree.
Right. The local limit is a skeleton tree. So how is this connected? Is this somehow connected to this result?
That will come later. This is not a uniform tree.
Right.
That's still the Erdos-Renyi, critical Erdos-Renyi, therefore Galton-Watson 1. But you have a good intuition. But if you look at the something else, then Grimmett's result will pop up. Surprisingly, not surprisingly perhaps, if you look at the internal structure of the largest that you already hinted out, it heavily depends on this giant component structure. So what is essential thing is the so-called two-core. It is kind of a very good way to look at the giant component, depending on your community. But usually, if you look at the sparse random graph from the combinatorics community, usually you look at the two-core and so-called kernel, and you build up the things. So two-core. What is the two-core? We will look at the two-core, not only the two-core of everything, but we will look at, we will look at only the two-core of the largest component. And sometimes two-core is defined as the subgraph of the whole graph whose minimum degree is at least 2. But because I'm restricting myself on the giant, we look at only the two-core of the giant. Yeah? So two-core in this talk will be the maximum subgraph of the largest component whose minimum degree is at least 2. If you haven't looked at it, because we have a different community, how you create such a two-core is you start from a giant component, you delete the leaves one after another, then you will reach the two-core. It's a so-called peeling process. Or in other words, if you look at how the things are attached, you will immediately realize that indeed the giant component consists of the two-core, in which every vertex in the two-core, which is depicted in green, are replaced by rooted trees. Rooted single vertex is also rooted tree, so like that. The giant component is indeed composition of the two-core together with rooted trees. Now, if we select one vertex uniformly random from the giant component, yeah, we restrict ourselves to be the fact that the root is chosen only from the giant component. Indeed, it will lie not in the core vertex, but outside. Why? Because there is yet another structural theorem saying that indeed the order of the two core in planar graph is sublinear in N. Again, comparison to the Erdos-Renyi, in the Erdos-Renyi, when the average degree is larger than 1, but constant, any constant, indeed two core is also linear in that regime. Yeah? Two core is born together with a giant. But in planar, the linear size two core is born indeed, not until average degree being 2. Perhaps I'll come back to that later, maybe somebody will ask. So anyway, in this regime, surprisingly, the two core is quite small. Therefore, if you select one vertex uniformly random, will not hit one of these with high probability. It will hit the vertex outside somewhere. Now come back to your question now. What we can do is the following. If we delete the edges in the two core, which are depicted in the blue, I delete it, what we get? Uniform random forest. Everything is uniform random forest. But the result that he was mentioning earlier is about tree. So now it has to do with how many components will be there, what is the size of the random tree in this forest. But one can also show, yeah, therefore it leads to the local limit of a random forest. It's not direct. Surprisingly, you need a couple of pages to go there because there are other details. It's not direct from the Grimet's result. So we have to a little bit be careful. So we will look at the random forest on n vertices with the T many tree components. T many, of course, this T number of tree components correspond exactly to the size of the two core. Yeah, I have only 5 minutes. Maybe I will be done soon. Now, if you select one vertex uniformly random, then it will lie in one of the three components, of course. But then the distance, what we can show is the following. If the number of tree component T is smaller order than n, sublinear, as in the two core, then indeed the distance between the root of the tree that contains the root of the forest is far away. Therefore, if you look at the omega, therefore, if you look at the local structure, we always look at the ball of finite radius. It's like looking at random tree. So n, as you said, so maybe I have to quote here. So due to the Grimet's result, we know that for any random uniform tree, the local limit is a skeleton tree. Sometimes you call it Caston tree. Therefore, you combine this together. I can wrap up, right? In the previous slide, if you select your vertex uniform random from the giant, the local limit will be T infinity. On the other, in the earlier slide, we saw that if you select one vertex, root vertex outside the giant, it's the Galton-Watson one. Now, if you select one vertex uniformly random from the whole universe with probability T minus 1, if it lands in the giant, with probably 2 minus T, it lands outside. That's how we prove things. So now wrap up the things. We have seen the phase transitions in Erdos and Renyi. I have still here GNM, but anyway, to compare directly. And I have a D because it's from other slides anyway. So uniform random graph had a very nice phase transition following the Galton-Watson tree. On the other, in a planar, there are two critical periods in between just linear. And we have also seen that the fragment of the Erdos and Renyi is subcritical. On the other hand, fragment of the random planar is critical. It's kind of interesting to me. And the second largest is therefore of order n to the 2/3, not the sublinear logarithmic. And furthermore, we have seen the local limit of this type. One of you might already seen why Mihyun restricts herself to D equals between 1 and 2. The reason being that I don't know how to do it. Even we know that it should be the two core threshold is when D is equal to 2, but we don't know how to prove things. Therefore, I don't know yet how to do this. Maybe some of you have a more direct way to deal with local limit when D is larger than 2, between 2 is. Yeah, thank you very much for your attention.
Thank you very much for this beautiful talk. Are there any further questions? Yeah, Shiva, take the microphone.
Is there a excursion viewpoint of the proofs? Like can you walk around the components and then?
That would be nice. But as I said, this model is quite new or unpopular, let's say. Popular model is the n vertex model. It's easier to handle, but kind of a dynamics on the random planar graph is not yet studied. Although in the very original paper by Steger, McDermott, and Welch I mentioned, they have defined this very nice Markov chain on the planar graph by just deleting or adding an edge subject to planarity. This dynamic is there, but nobody knows the mixing time of such a simple Markov chain event.
I have a simpler process on it. If you had, instead of P and M, you had P and P,
Yeah.
P, then we could actually say, let's say D is 1.5.
Yeah.
I could do percolation with probability, I don't know, 3/4 or something, and I'm still in the region where I have a giant.
Yeah.
So what happens here if on top of your graph, D is 1.5, you do percolation with some 1 minus epsilon, where you just keep edges with this probability
Yeah.
1
So-
minus epsilon and delete them with probability epsilon.
We haven't think about it. Maybe it's one way of doing that. So if I return to the original model P and P, let's say, in order to study that, what you have to know is is there a concentration result on the number of edges in P and P? It's heavily dependent on model because of we don't know how many edges are there. So simply what you can do is G and P subject to planarity. If you write down all these cooking things, cooking recipe, then what it boils down is that you can study G and P subject to planarity and subject to its number of edges. So the subject to number of edges in P and P is not easy. We have a conjecture, but it's not that easy. What is even the expectation? What is the expected number of edges in P and P when P is about D over N? It's not easy. It's a strange number. It's E2 minus E times. There is a conjecture due to the kind of counting. As you can smell here behind the scene, we are counting a lot of things using the so-called combinatorial Laplace method. We count things very, very precisely. And out of this counting formulae, we have the conjecture on the expected number of edges in P and P. If you can do that, I think things will be easier, but we don't know. And in terms of this percolation, perhaps on Gn, M now, still, yeah, I don't know. Maybe I have to work on it. I haven't think about it percolating on planar P and M, but P and NP will be difficult.
All right, maybe in the interest of time,
Yeah.
let's thank Mihyun once more.